So let's start with the webinar. Today is everything about production line testing of audio devices. Let's have a look at the agenda for today. We'll discuss some of the basic challenges that you can find in a production line environment. I'm also going to present a solution from GRAS, the AL30 acoustic test chamber. Then we're going to discuss a new production line microphone called the GRAS 40 PM with EQSet technology. So I will explain what is it about with the EQSet technology and what's so revolutionary about it. Then my colleague James will introduce into the APX 500 software, the APX 517 analyzer and APX 500 Flex analyzer. And we'll look at some of the main functionalities made towards production line testing. And then by the end of the webinar, we'll have a system demonstration using different elements shown today during this presentation. Last but not least, we'll have some time for questions and answers. So first of all, very short introduction about the companies. We can say that both Audio Precision, AP, and GRAS can be considered as trusted advisors when it comes to audio device testing. GRAS itself has more than 25 years supplying acoustic sensors and test fixtures and other devices for acoustical testing for the industry, while AP has more than 35 years of supplying state-of-the-art analyzers and software, originally for electronic audio testing, but nowadays also for electroacoustical testing. The audio industry has experienced a tremendous growth during the last 2 decades, and we can say that both GRAS and Audio Precision, as part of the Axiometric Solutions Group, have been involved in every step of the way designing equipment to fulfill our customers' needs. Here in this slide, you can see just some of the long list of customers that have been working with us over the years and providing valuable feedback to us. Now let's discuss some of the challenges that we can find in a production line environment when it comes to testing audio devices. First of all, I would like to talk about efficiency and reliability because these are very common topics. I mean, we would like to test as much equipment as possible in the least amount of time, but of course, we also want to do it in the most reliable way possible. And therefore, we need to find a balance between these elements. Reducing too much the testing time might lead to unreliable results, but also using the wrong equipment for the task will affect both parameters. On the second, we have easy to operate equipment. We don't want to use too much time in order to train the operators to get reliable and repeatable results. So it is actually very important to reduce the test setup complexity in order to meet this goal. Another thing to consider is the background noise. This is particularly challenging when it comes to acoustical testing. We're thinking about the production line, and we have a lot of people and a lot of machinery creating a lot of noise. And of course, we don't want this noise to interfere with the testing, because that will degrade the quality of our test results and create the need of repeating measurements and lose valuable time, and we don't want that. We also need to consider the test noise. This is a noise generated by, of course, the test itself, and it will disturb the environment around this testing area, around our test bench. That means that our operator might be disturbed, and we need to protect the operator from the test noise. We can also be disturbing another test being executed in another test bench close by to our testing area. So we need to try to tackle this issue as much as possible. Then, of course, we need to consider the cost of operation. Every hour that a production line is running will cost us money. But also all the time that our production is not running because of production issues like broken test equipment, such as test fixtures or microphone, or unreliable test equipment, that would also cost us a lot of money. Therefore, it is of paramount importance to reduce the production downtime as much as we can. On the last item, I want to talk about comparisons against R&D targets. And this is important because the equipment that is used to test devices in an R&D environment is different than the equipment used in a production line. This means that we can't rely on target curves or tolerances specified in research and development and then copy paste them to a production line. We are not going to talk about this particular topic during the webinar, but I'm going to leave a link here that you can click from the PDF that you have in the handout sections, and you can find some examples related to this particular topic, in particular talking about going from let's start with the webinar. Today is everything about production line testing of audio devices. Let's have a look at the agenda for today. We'll discuss some of the basic challenges that you can find in a production line environment. I'm also going to present a solution from GRAS, the AL30 acoustic test chamber. Then we're going to discuss a new production line microphone called the GRAS 40PM with EQSET technology. So I will explain what is it about with the EQSET technology and what's so revolutionary about it. Then my colleague James will introduce into the APX 500 software, the APX 517 analyzer and APX 500 Flex analyzer. And we'll look at some of the main functionalities made towards production line testing. And then by the end of the webinar, we'll have a system demonstration using different elements shown today during this presentation. Last but not least, we'll have some time for questions and answers. So first of all, very short introduction about the companies. We can say that both Audio Precision, AP, and GRAS can be considered as trusted advisors when it comes to audio device testing. GRAS itself has more than 25 years supplying acoustic sensors and test fixtures and other devices for acoustical testing for the industry, while AP has more than 35 years of supplying state-of-the-art analyzers and software, originally for electronic audio testing, but nowadays also for electroacoustical testing. The audio industry has experienced a tremendous growth during the last 2 decades, and we can say that both GRAS and Audio Precision, as part of the Axiometric Solutions Group, have been involved in every step of the way designing equipment to fulfill our customers' needs. Here in this slide, you can see just some of the long list of customers that have been working with us over the years and providing valuable feedback to us. Now let's discuss some of the challenges that we can find in a production line environment when it comes to testing audio devices. First of all, I would like to talk about efficiency and reliability because these are very common topics. I mean, we would like to test as much equipment as possible in the least amount of time, but of course, we also want to do it in the most reliable way possible. And therefore, we need to find a balance between these elements. Reducing too much the testing time might lead to unreliable results, but also using the wrong equipment for the task will affect both parameters. On the second, we have easy to operate equipment. We don't want to use too much time in order to train the operators to get reliable and repeatable results. So it is actually very important to reduce the test setup complexity in order to meet this goal. Another thing to consider is the background noise. This is particularly challenging when it comes to acoustical testing. We're thinking about the production line, and we have a lot of people and a lot of machinery creating a lot of noise. And of course, we don't want this noise to interfere with the testing, because that will degrade the quality of our test results and create the need of repeating measurements and lose valuable time. And we don't want that. We also need to consider the test noise. This is a noise generated by, of course, the test itself, and it will disturb the environment around this testing area, around our test bench. That means that our operator might be disturbed, and we need to protect the operator from the test noise. We can also be disturbing another test being executed in another test bench close by to our testing area. So we need to try to tackle this issue as much as possible. Then, of course, we need to consider the cost of operation. Every hour that a production line is running will cost us money. But also all the time that our production is not running because of production issues like broken test equipment, such as test fixtures or microphone, or unreliable test equipment, that would also cost us a lot of money. Therefore, it is of paramount importance to reduce the production downtime as much as we can. On the last item, I want to talk about comparisons against R&D targets. And this is important because the equipment that is used to test devices in an R&D environment is different than the equipment used in a production line. This means that we can't rely on target curves or tolerances specified in research and development and then copy paste them from to a production line. We are not going to talk about this particular topic during the webinar, but I'm going to leave a link here that you can click from the PDF that you have in the handout sections, and you can find some examples related to this particular topic, in particular talking about going from R&D to production line testing in headphone testing. So the first solution that I would like to discuss today is an acoustical test chamber made by Grass that will help you solving many of the challenges mentioned before. It will help you improving the efficiency and reliability of your acoustical testing in a production line environment, and will also reduce the impact of the background noise on your test and also protect the operators from the test noise. All of that with a solution that is easy to use. So we basically have a very small, or a relatively small acoustical test chamber that is helping us isolate the background noise from the environment around the test chamber, but also will keep the test noise inside the chamber. We have a drawer on the front that will help us with quick device under test exchange. On the bottom, we also have shock and vibration isolation fit. And it's a solution that can be used for quick and reliable tests of phones, tablets, loudspeakers such as speaker phones or smart speakers, or any other similarly sized acoustic device. On the bottom of the screen, you can see a graph showing 10 consecutive measurements performed with the same device under test inside the AL30. As you can see, the 10 measurements are practically seen as the same curve. And this is just to show you that the AL30 is the perfect device to get repeatable results. Here we can see more pictures of the AL30. As we can see in this picture over here, on the back of the AL30, we have a big opening. Inside, we have acoustical dampening foam that will help reducing the amount of reflections, acoustical reflections inside the chamber. When we open the door, it's going to be easier for the operator to set up equipment inside the test chamber. So if we see this picture here, inside the AL30, we have different mounting points on the top of the box and different mounting points on the bottom. These mounting points can be used to set up measurement microphones or a sound source. And here we can see that we have a measurement microphone on the top, a measurement microphone on the bottom, and a mouth simulator that is being used as a reference sound source. On the front of the AL30, I already mentioned we have the drawer, and when we open the drawer, we can see that we have rails. These rails have rulers that can be used to position the device under test in a specific position, and then we can recall this exact same position to be repeated in a different production line, for example, or in a different AL30. We have 3 different versions of the AL30, version 1, version 2, and version 3. All of them have the same weight and the same overall dimensions. The only difference, or one of the main difference, being the size of the drawer, the size of the opening of the drawer. And this will give us different top clearance between the different versions. So depending on the size of the device that you want to test, you will pick one version or the other. You've probably seen in other pictures that on the side of the AL30, we have a connector panel. This connector panel will act as an interface between the inside of the chamber, where we have our device on the test, and the outside of the chamber, where we have our analyzer or data acquisition system. The connector panel can be customized with different connectors, and here we have a list with all the connectors we have available. If your connector of choice is not on this list, we can leave a blank plate on one of these connectors so you can add your connector of choice later. The AL30 version 1 will give you the possibility of adding 8 customized connectors, while the AL30 version 2 and 3 will give you the possibility of adding up to 10 customized connectors. The AL30 comes with different accessories, so you can pick different accessories depending on the device and the test you're using. First of all, you can pick between different device and the test holders. These are mounted on the drawer, as you can see in this little animation up here. So some of these device and test holders will hold the DUT in a lower position compared to the others. This will give you a higher top clearance from the top of the drawer. We also have different microphone holders. As you can see here, we can mount these holders inside of the chamber on the bottom and top mounting points, or we can mount the microphones directly on the rails of the drawers, as you can see on the top right corner of this slide. We also have other accessories, such as the OP45 we see down here, that can be used to mount reference loudspeakers. In this case, it's pictured with a mouth simulator, the GRASP 44AA or 44AB, that can also be used as a reference loudspeaker. Here we have an example setup where we have measurement microphones mounted inside the drawer, inside the chamber, sorry, but also mounted directly on the drawer. We are testing a small tablet, as you can see, and we are using a mouth simulator. On the outside, we have the analyzer that is connected to the device on the test via the connector panel on the side of the chamber. Once the cabling is finished, when everything is set up, we can just close the drawer and start with the test. On the right side of the screen, you can see the information about the AL30's self-insertion loss. This is how much of the noise the AL30 is able to attenuate. On the top of the screen, You have links for more information for the AL30, including a product video, the brochure, and a link to the website for more information. The second solution that I would like to present is the GRAS EQ40PM, which is a miniature production line microphone. As you can see in the picture, this is a very small quarter-inch microphone with just 34 millimeters in length. If we look at the basic specifications, we can see that this microphone is optimized to work in the audible range from 20 hertz to 20 kilohertz with a sensitivity of 25 millivolt per Pascal, with a very tight tolerance in this specification, just plus minus 0.2 dB for the sensitivity. The noise floor is around 30 dBA. The upper dynamic range limit or acoustic overload point is set at around 120 dB SPL. This is measured with 3% distortion. We're going to talk further about environmental stability in another slide, but we can say that it's better than 0.3 dB. The microphone is powered using a CCP power supply, which is one of the most common microphone supplies used with test and measurement equipment. ICP, IEP, CCLD are other names for compatible technologies. So if you have a data acquisition system or analyzer that has IEP or ICP or CCLD microphone power supply, it means that it's going to be compatible with our EQ40PM microphone. We have a SMB connector, as we can see here in the picture, but the most relevant thing about this new GRAS microphone is the EQset technology. I will introduce this technology in a second, but before I want to discuss what is the target for this microphone. As I mentioned before, I call the EQ40PM a production line microphone. And this is to differentiate this microphone from measurement IEC standardized measurement microphones. So production line microphones, or sometimes called quality control microphones or QC microphones, are cost-effective microphones used in a production line environment. The GRAS EQ40PM is meant to replace microphones like the ones we see here on the left. These are very, very popular, cost-effective microphones. This new microphone, the EQ40PM, has the same dimensions, the same connector, and is powered in the exact same way as these two microphones we see on the left. It means that the EQ40PM can act as a direct replacement for these two microphones we see on the left. Now let's talk about this EQset technology. We consider this a revolutionary technology from GRAS, which is going to be a game changer for all production lines out there requiring microphones for the tests. This is a patent pending technology. The concept is that we keep 100% analog sensor, but with built-in electronics that will allow for the correction of both the gain, that will be the sensitivity of the microphone, but also the frequency response using an equalizer. So the microphone is capturing this acoustical signal. We are transforming this analog signal into a digital domain. And with the help of digital signal processing, we are adjusting the gain, but also the frequency response of the microphone. Before sending the signal to the output of this microphone set, we are converting the signal again into the analog domain. All these electronics are miniaturized to fit inside this very small form factor, and we call it a transparent technology from the user's perspective because it doesn't require any changes in your signal change or any input from the user. You can just use your existing interface. The GRAS EQ40PM is the first microphone that comes with this EQSet technology, where we are planning to introduce more microphones in the future with the EQSet technology. Hopefully, this next slide will help us understand why microphones with EQSet technology, like the Graz EQ40PM, are so much better than your standard production test microphone. So first, let's see what happens with a typical way of working. In this case, let's say we get 100 different microphones to work in different stations in our production line. As you can see, the sensitivity and the frequency response of this microphone is all over the place. And therefore, we'll need to adjust the sensitivity, compensate the different sensitivity for these microphones. And we can do that by performing an acoustical calibration or by relying on TETS technology, for example, transducer electronic datasheet. Then we'll have to do that for every microphone one by one in our production line. But if we look at this graph over here, we can see that this adjustment is only performed at a single frequency, which is typically 250 Hertz or 1 kilohertz. But we still have a big differences in the frequency response of all the different microphones in the rest of the frequency range. This is not very common, but sometimes we'll use equalization by post-processing the data in order to correct for this. But then this will take a lot of time because we'll need to consider the differences in the frequency response of every different microphone and adjust every different microphone one at a time, which is really time consuming and it's typically not done in a production line environment because of this. Now let's see how this process compares to a microphone with the EQSet technology. As we can see, right out of the box, we get 100 different microphones with practically the same sensitivity and practically the same flat frequency response from 20 Hertz and up to 20 kilohertz. That means that we are not going to require the use of our valuable time in order to adjust every microphone in particular. And the same equalization is not going to be required. Every microphone is practically the same to the other. So what's the meaning of all this? Well, basically, that your measurement uncertainty is much smaller and you won't have to use valuable time of your production in order to adjust for sensitivity or frequency response differences between one microphone or the other. I know that here in this slide we have a lot of information, but if we pay attention to here on the left, we can see the tolerances in the frequency response of a typical production line microphone. These are great microphones. These are great microphones, but they're relying on an older technology without the benefits of the EQSet. So you can see that the frequency response can be anywhere in between this red area. And when it comes to the sensitivity itself, usually specified at 250 Hertz, you can have a variation up to ±2 or ±3 dB from one microphone to the other. Then again, we can use an acoustical calibration with a piston phone or a sound calibrator or rely on TETS for calibration, but we are only going to be adjusting the frequency response and sensitivity at one single point without considering the rest of the frequency range of the microphone. Once again, if we compare this with the tolerances in the frequency response and sensitivity of the EQ40PM, we can see that the tolerances are much tighter. And this is why we are not going to require TETS any longer for calibration if you were doing that. as every microphone is practically the same in terms of sensitivity and also frequency response. Once you adjust your signal chain for one of our GRAS EQ40 PM, you can exchange it for another one without the need of making any adjustments. This GRAS EQ40 PM makes a great match with an APX517 analyzer from Audio Precision, which is optimized for acoustical measurements in a production line environment. James is going to tell you more about it in a bit. But it's also a great match with inexpensive audio interfaces, like the one we see on the bottom of these slides. So this can be combined with an Audio Precision Flex key to be able to use the APX 500 software with third-party hardware. From my previous slide, you might ask yourself, how come you can use a GRAS EQ40 PM directly with an inexpensive audio interface when I mentioned before that the EQ40 PM has to be powered with a CCP power supply? Well, the thing is that this microphone is also compatible with plus 48 volt phantom power supplies. In order to use the GRAS EQ40 PM with a plus 48 volt phantom power supply, you have to use a test setup like this one, relying on an BNC to XLR adapter like the GRAS AG3. So if you have an inexpensive audio interface with XLR inputs and plus 48 volt phantom power, with such a setup, you're going to be able to drive the GRAS EQ40 PM. So a microphone using the EQset technology, like our 40 PM, does not require the use of TEDS, transducer electronic datasheet, because every microphone is the same. That means that the sensor identification is also not necessary. Nevertheless, if you still need to identify each microphone, all the 40 PMs have a serial number on the side, but also a barcode. So you could actually use a barcode scanner for your sensor identification in your production line if that's needed. At GRAS, we developed this new EQ40 PM microphone so it's easier to produce compared to IC standardized measurement microphones. This means that production line at GRAS is optimized to produce the EQ40 PM in big quantities if needed. Therefore, we have a short delivery time for this microphone, even for big quantities. This microphone can be delivered in boxes of 1, 12, or 24 pieces. So the ordering can be as flexible as possible. You know, every microphone is affected by environmental condition changes. That is, changes in temperature, changes in static pressure, and changes in humidity. Even IEC standardized measurement microphones get affected by these changes. Then typical cost-effective production line microphones are even more affected by environmental changes. And here we have an example of that, where we are comparing a typical production line microphone, like the GRAS 40PK, a cost-effective production line microphone, and we can see what happens when we change the temperature from 10 degrees Celsius, then up to 45 degrees Celsius, and then again down to 10 degrees Celsius. We can see how the sensitivity of the microphone is changing dramatically. Behavior like this is typical in every cost-effective production line microphone, not only with this GRAS unit. The good news here is that with the EQ40 PM, you are not going to have this problem. And here we can see the result of the sensitivity variation when the microphone, the EQ40PM, is exposed to the same temperature variation. And we can see that the sensitivity drift is minimal. This is also important to consider when you have production lines set up in different parts of the world with different temperature, with different environments, such as different temperatures or a different static pressure. If you have microphones that are affected considerably by these environmental changes, then it's going to be more difficult for you to compare results that you obtain in one production line compared to another production line in a completely different part of the world. So overall, when it comes to the Graz EQ40PM, you have a microphone with a very competitive price. We are not talking prices here, but you're welcome to contact your sales representative and get information about pricing. As I mentioned before, compared to other production line microphones, the EQ40PM, it's environmentally stable. It's very easy to set up because we are relying on the same power supply and the same connectors as the typical production line microphones. It's easy to replace because there's no difference between microphones. So if you break one of these EQ40PMs, you can replace it without the need of adjusting your signal chain or readjusting your signal chain. You can also use EQ40PM with entry-level audio interfaces with plus 48 volt phantom power. And all of these things will help you minimize measurement errors and reduce the uncertainty of the measurements. We can provide the EQ40PM in big quantities with a short delivery time. You have the barcode for easy identification of each sensor. And here at the bottom, I'm leaving you with a link to an interesting article and calculator that we have online at the Graz website, where you can calculate how much is the microphone calibration costing you, taking into consideration how much time you're using a production line to calibrate your sensors. On the right side of the screen, I'm also leaving some extra information if you want to learn more about this product. And now I'm going to let my colleague James continue with the presentation.
Hi everyone. So I'm just going to take you through a few slides on information on our production line solutions for audio and acoustic measurement, and then we're going to run an example project file on my mobile phone, and we're going to do this entirely or almost entirely with acoustic, both commands and measurements. So if any of you attended this production line test of audio devices webinar earlier in the year, you might remember that we used a APX 500 Flex and an RME Fireface product to run these measurements. Today we're going to be using the 517. The 517 meets all the key requirements for production test. It's fast, it's easy to set up, especially using the 40PM EQ set microphone. It's proven reliability, keeps the production line up and running, and it's priced to fit on the production line. As Santiago said, we're not going to be discussing pricing, but certainly one thing you may be interested in taking advantage of at the moment is that the 517 actually comes with a free of charge 40PM microphone at the moment. So typical devices under test that you might test with APX 500, either Flex or 517, include headphones and headsets, speakers, microphones, and devices with speakers and microphones, such as today's device under test, the mobile phone. Earlier in the year, we tested a tablet, but smart speakers and smart devices and any consumer electronics. So the APX 500 software is a powerful and fast interface, can provide one-click measurements, automated reports. You can create code-free automation using our measurement navigator and our sequence mode options. But if you need to get more involved, we do have a full API into our APX 500 software. So you can control this from environments such as VB.NET, C#.NET, MATLAB or LabVIEW, and Python using the PythonNet module. You can lock projects and create a simplified user interface very, very simply using our software and our production test modes. So firstly, a little bit about the 517. There's a link on this slide in the PDF handout with more information. But the 517 is a 17025 accredited acoustic analyzer. It comes with a single channel power amplifier, a 2-channel headphone amplifier, 4 microphone inputs, 2 which are CCP powered and 2 which are phantom powered. And then we have a digital I/O option, which you can choose. In the image here, we've got a Bluetooth Duo module fitted, and it's a very, very popular configuration. So as we mentioned before, everything you need to test the speaker, microphone, headphone or headset in one box. It's optimized to drastically reduce test time. It's a 2-channel analyzer and makes reliable and accurate measurements a very simple thing to accomplish. So I'm also going to mention the APX 500 Flex because we're focusing this webinar on production line testing. Again, it's a very aggressively priced solution, which enables users to use the APX 500 software with third-party audio devices via our ASIO interface. So an example here, you might have an RME product. In the image here, we have an RME Fireface. And for example, one of the things you need to consider if you're using this with Flex and the 40 PM is you need to be able to configure the device to turn on the 48-volt phantom power. So here you can see from the tools options in the software that comes with the RME that you can turn on 48-volt phantom power on these 2 mic inputs. These are balanced inputs with 48-volt phantom power, and then using the XLR to BNC adapter, you can power the 40 PM. So regardless, once you've chosen your interface, whether it's a 517 or in this case showing on the screen a Flex, you can choose your connector, whether that's a mic input or in this case the ASIO, and using the Fireface USB, you can then connect your microphone or microphones, set the sensitivity, and for the 40 PM we can simply choose our sensitivity as 25 millivolts per Pascal, and then if we choose not to use the 40 PM, we can actually see we need these additional steps to calibrate the two microphones. And this again is our time saving and money saving solution. So if you use the 40 PM, there's really no need for a sequence at all to calibrate the mics. And typically in a production environment, this would be carried out by a technician level employee. So again, using the 40 PM, you can just leave the production line with a standard operator to run the projects. And there's an image here with the individual sensitivity of the two mics shown on the right hand side. Whereas when we use the 40 PM, we've got the same sensitivity and no calibration required. So one thing to consider, both dependent on your device under test, but also if you're using a Flex product, will be your audiophile settings. So your ASIO device may only support certain sample rates, but certainly if you're measuring something like a smart speaker or a mobile phone and you're generating a file to be loaded onto a device, either a smartphone or a mobile phone or a tablet, you need to consider the sample rate supported by that device. So for example, here you can see a default with the APX of 192 kilohertz, but you might want to change this, and there's several ways you can do that. So with our open loop continuous sweep options, you can change it in the user interface that you can see. You can set pilot tone frequencies and start and stop frequencies for your sweep. And then you can also configure levels for both the pilot tone and the sweep tone. So all of these should be considered, and you can even apply an EQ. And then once the configuration is complete, you can simply click on generate and save a file to be uploaded to the device under test, which later on we'll be using, and we'll be asking our device under test to play such a file. So here you can also configure duration of each tone. So we've set levels and frequencies, and then we can set duration. So this really is a configuration so that APX knows what to expect from a device under test. And then when you're actually making the measurement, you can set an appropriate trigger, and this might be a level, and you can set this so you don't trigger on some random noise on the production line, but also so you can make sure it's at a level that's appropriate for the measurement. as I said, once that's complete, you click on generate. And certainly with the device we're testing today, probably the most cumbersome task is getting this file onto the mobile phone we'll be testing. And we're not going to be taking you through that. And certainly manufacturers of these devices will have simple methods to be able to do this, and could even produce a device with a phone or with a tone or a audio file already pre-programmed. So other open loop measurements are things like multi-tone. And again, just an example here of how you can view these, the sample rates, and how you can create a WAV file for loading onto a device under test. And then if you need to change things like the sample rate, how you can do this in APX software. So open loop measurements are not new for APX. They've been around a long time. The two examples, the log chirp, so the open loop continuous sweep or acoustic response, or the open loop multi-tone measurement, are two of the fastest measurements to obtain frequency response and additional information such as distortion and noise. So looking at our demonstration of the measurements today using 517, the AL30, 44AA mouth simulator, and the 40PM microphone with my mobile phone. We have a graphical representation here of what we have in the way of setup. And then I have some additional slides as to how we're going to achieve this. So I'm going to use a simple signal acquisition measurement to play a file. So this is a pre-recorded file of my voice asking the mobile phone to play a file that's loaded into my music application on my mobile phone. So this is just a passage of my voice instructing the phone to play the generated file that we generated from our continuous sweep in open loop mode, which I've already uploaded via iTunes onto my mobile phone. Then we're going to, when the device under test plays the file, we're going to acquire the signal via the 40PM. Once we've done that, we're actually going to use the device under test to record the same file, which we're going to play through our mouth simulator and record onto the device under test. And to enable this, we've created a shortcut on the device under test. So the shortcut uses a record audio instruction and then followed by a save, and it saves it to a location in the shortcuts folder. And then what we do in our subsequent measurement is we analyze the recorded file. Now we do have a rather long delay while we wait for this file to sync with my iCloud drive so that we can actually analyze the recorded file. Now, I'm certainly not suggesting that this would be the way a manufacturer of this device would do this. They'd certainly have a faster way to access that recording than waiting for the iCloud to sync. But it's just an example of what you can use with APX to actually measure the response of the microphone input on the mobile device. So with that said, I'm going to switch to my software. And I'm going to run this sequence, and then we can look in detail at the sequence steps. So it prompts me to enter a serial number. And then it prompts me to place the mobile phone in the holders in the AL30, which are positioned suitably at the right distance away from our 40PM microphone. And you probably won't be able to hear this because it's inside the AL30, but this is my voice telling the mobile phone to play our generated 5-second chirp WAV file. And there you can see we've acquired the response. And now I need to open the drawer and press my shortcut to record. Then I can continue. Now we're generating a sweep, including a pilot tone. That's very important to be recorded by the device. And now we have our rather long wait time while our file syncs with the iCloud for us to analyze the file. And there you can see our result. So here you can see we get our RMS level. We can smooth that. But most importantly, we can get our acquired waveform. Now, at the moment, this acquired waveform is not only the response of the microphone, it's also the response of our mouth simulator. So if you measured your mouth simulator previously, you could in fact equalize your results. So your relative level, for example, you could add a derived result and EQ that with the response curve of the microphone. I'm not going to do that today, just it's a possible solution. But here, really, this is just a functional test of the mobile phone, both the microphone input and the loudspeaker output. So if we look at this in a bit more detail, you can see the steps required. So in here, we have a prompt asking me to enter the device serial number, and it simply appears on the screen like this. And let's see, here we have our prompt to place the mobile phone in the AL30, and we have an image and we have some text, and it appears together such as this. And this is what we saw when we run the project file. And then here we have our signal acquisition, which simply plays this file that we recorded, asking it to or asking the mobile device. So this is my voice just saying, "Hey Siri, play 5-second chirp." And the following measurement actually acquires the data. So this is an open loop measurement, and it will wait for a pilot tone. And I've set a level threshold of 6 Pascal. And if we look at our acquired waveform, you can see that meets our threshold for our 1 kilohertz pilot tone. And you can see, just looking at the acquired waveform, that when we actually play the file and measure it, that we have pretty much no bass response. And then when we get to, say, 3 seconds into the chirp, we start building in level and get our response as shown. Obviously, these levels will depend on how close you place your microphone to the device under test. But we get a nice impulse response. And then when we continue on our sequence, we then have a signal acquisition here where we're actually playing a 5-second chirp after we've set our device to record. So we start the record. This will automatically record for 10 seconds. That's set up in the shortcut. That's much longer than the actual file, the 5-second chirp. And then we change signal path because we've acquired the data. We've waited for our 10 or 15 seconds, however long it took. And then here you can see we're analyzing a file in my iCloud drive. And then we create a report. Not much to go wrong here because I haven't set any limits on any of these measurements, but you can see you get all of that data generated in a report. Options, as we discussed, to lock a project. I can lock a project with a simple password, and I can put it in production test mode. I can even choose not to show APX, but I will show it in this case. And we get a banner image, and we get a button that runs the sequence. Let's unlock that again and just show you another feature. So you can have multiple sequences, and those buttons for the different sequences will just appear when you put it in production test mode. Some of the other features, you can choose what's displayed on the screen and actually what information you save, both in variables and in statistics. So in production test mode, these will continually update and appear on the screen along with the measurements that are being run. So with that, I'd like to ask if there's any questions. I can't see anything in the...
Thank you, James. We are a bit over time. We do have some questions. If we can't answer all of them, we are going to answer them privately via email. Someone here is asking, what if I can test my device with sine-based signals?
Okay, well then transfer function is an excellent option. And transfer function is a measurement. I won't add it to the, let's just add a measurement here. So transfer function is a measurement where you could use something such as noise as a stimulus. You could even use an audio file. It could be the IEC speech. And very, very simply, the only thing you need to consider when you're using transfer function is that the response data that you get out, the bandwidth of the measurement effectively, will depend on the signal that you use. So if you're using, let's say, narrowband speech, you'll probably only get frequencies up to 4 kilohertz. So it's important to remember that the stimulus and the acquired data need to cover the bandwidth that you're interested in. And again, if you go to the website, the AP website, you can just search transfer function, and there'll be heaps of information there as to how you can use transfer function to measure your acoustic devices.
Okay, we have another question. Is there a way to measure loudspeaker force factor in a single step test?
Force factor?
Yes.
Which is?
I think we might need further clarification.
Yeah. It's called BL. What does BL stand for, Lorenzo?
I think we can clarify this over email, if that's okay.
Yeah.
Yeah. Someone is asking if we are going to share the project file.
We can share the project file. That's not a problem.
Good. Yes, you have our emails on this presentation, so you're welcome to contact us if you have further questions. We have another question here. 40 PM microphone, a free fill or a pressure microphone? It's actually a pressure microphone. It's optimized to measure devices that are close coupled to the microphones, a very short distance, so you can use it to measure loudspeakers, or in this case, it placed very close to the loudspeaker of our mobile phone, for example. But as I mentioned before, we are planning to release other GRAS microphones using the AQSET technology in the future.